In 1901, off the coast of the Greek island Antikythera, sponge divers pulled a corroded bronze lump from a 2,000-year-old shipwreck. For decades, no one knew what it was. Then, in the 1970s, X-ray technology peered inside and revealed a complexity that should not have existed in a device from around 100 BCE. Inside was a sandwich of interlocking gear wheels with triangular teeth, arranged to compute the cycles of the heavens. This was the Antikythera Mechanism, an analog computer, a mechanical calendar that predicted the positions of the sun, moon, and the 5 planets known to antiquity, forecast eclipses, and even tracked the 4-year cycle of the Olympic Games. Its makers understood the moon's uneven motion, the 19-year Metonic cycle, and the 83-year Saros cycle of eclipses. They machined bronze gears with a precision not seen again in Europe for over 1,000 years. This was a programmable, differential gear-driven instrument that, by modern reconstruction, could show the moon's phase, the rising and setting of key stars, and the timing of Pan-Hellenic festivals. The existence of the Antikythera Mechanism forces us to rethink the entire history of science. Greek engineers in the 1st century BCE possessed a level of mechanical and astronomical knowledge once assumed impossible. That device was not a fluke, it was the product of a lost tradition. But if such sophistication survived even in fragmentary form, how many other devices have crumbled into dust or still rest beneath the sand and sea? That single corroded lump opens a door onto a forgotten landscape of ancient ingenuity. To walk through that door, we must travel across continents and back through millennia, from the stone circles of northern Europe to the desert observatories of the Andes, from the clay tablets of Babylon to the water-driven clocks of China. And we begin in Germany in 1999, when treasure hunters with metal detectors uncovered a bronze disc near the town of Nebra. It was dated to around 1,600 BCE, roughly 1,000 years before the Antikythera Mechanism was built. Across its dark patina, gold symbols had been hammered into the metal, a large circle, likely the sun or a full moon, a crescent moon, and a cluster of smaller dots. Those dots are unmistakably the Pleiades star cluster, a group the ancient Greeks called the Seven Sisters, and that farmers across Eurasia used to mark the start of the growing season. This was the oldest known representation of the cosmos created by human hands. The Nebra sky disk is not just art. Archaeologists interpret it as a functional sky map, possibly used to synchronize the lunar and solar calendars, a perennial challenge for ancient societies. The fact that the Unetis culture, a Bronze Age people in Central Europe, produced such an object challenges the assumption that complex astronomy began with the literate civilizations of Egypt and Mesopotamia. Here was a society we once considered primitive, creating a precision tool for understanding the heavens. The Nebra disk is proof that the drive to map the stars is older and deeper than we ever imagined. If the Nebra disk raises the possibility that Bronze Age Europeans understood the sky, Stonehenge forces us to ask that question of a far older time. The first stones were erected around 3,100 BCE, meaning the site was already ancient when the Nebra disk was hammered into shape, and its alignments are unmistakable. The main axis points directly toward the summer solstice sunrise and the winter solstice sunset. That much has been known for centuries, but it is the lunar cycle that may reveal the deeper purpose. Around the edge of the monument lie 56 pits called the Aubrey holes. The astronomer Gerald Hawkins proposed in the 1960s that these holes formed a computer of sorts, a way to track the 6-year cycle of the moon and predict lunar eclipses that recur every 56 years. The theory remains debated, but the numbers fit too neatly to ignore. 56 is exactly 3 cycles of 18:6, and Stonehenge was modified multiple times, as if the builders kept refining their celestial instrument. What matters is the scale. This was not a handheld device. It was a landscape carved into a cosmic tool, and Stonehenge was not alone. The passage tomb of Newgrange in Ireland, built 500 years earlier, aligns perfectly with the winter solstice sunrise. Across the British Isles, Neolithic people were embedding astronomical knowledge into the bones of the land. But aligning stone with sky requires observation passed down through generations without written records. That knowledge had to be preserved in ritual and memory. Meanwhile, in Mesopotamia, a different kind of preservation was taking root, one that would make the motions of the planets permanent on clay. In the ancient city of Babylon, scribes pressed wedge-shaped marks into wet clay tablets, creating records that would survive millennia. By the 7th century BCE, Babylonian astronomers were keeping systematic, daily observations of the sky. The astronomical diaries recorded the positions of the moon and planets, the timing of eclipses, the dates of solstices, all in a disciplined, repeating format. They built mathematical models to predict future celestial events. The key was the sexagesimal number system, base 60, which we still use for minutes and seconds today. With it, they could handle complex fractions and long cycles. The most famous of these cycles is the Saros, a period of about 18 years and 11 days after which the Sun, Earth, and Moon return to roughly the same alignment, making eclipses predictable. The Babylonians identified that cycle and used it to forecast lunar eclipses with reliable accuracy. Their predictive text series, like the Mole, a pin, compiled star lists and heliacal risings, the first visible appearance of a star before sunrise, which allowed them to build a functional calendar tied to actual celestial events. They could calculate the first visibility of the new moon, a critical skill for regulating their lunisolar calendar. This was repeatable, verifiable science, not mystical guesswork. The measurements were precise enough that centuries later, the Greek astronomer Hipparchus used Babylonian eclipse records from as far back as the 8th century BCE to refine his own models. When he compiled his star catalogue, he relied on data collected by scribes speaking a different language on the other side of the known world. That knowledge had traveled across cultures. But the clay tablets themselves were lost to time, rediscovered only in the 19th and 20th centuries. When modern scholars finally deciphered them, they found predictive methods that would not be matched in Europe for over 1,000 years. The Babylonians left us their system of thought written on clay, but what about the cultures that carved the sky into stone temples, embedding astronomical knowledge in sacred architecture? That question leads us to Egypt, to the Hathor Temple at Dendera, and to one of the most debated celestial diagrams ever found. Sometime during the 1st century BCE, on the ceiling of a small chapel, Egyptian sculptors carved a circular relief now known as the Dendera Zodiac. It shows the familiar figures of the zodiac, Aries, Taurus, Gemini, and the rest, arranged in a circle surrounded by other celestial symbols. Planets appear as figures in boats, and the ecliptic, the sun's yearly path, is clearly marked. Even the Milky Way may be represented, wrapping around the disk like a celestial river. The problem is that the classical zodiac, the one with the ram and the bull and the scorpion, is a Greco-Babylonian creation. It was not native to Egypt, so how did it appear in a temple dedicated to the goddess Hathor, built in the Ptolemaic period when Greek rulers controlled Egypt? The answer almost certainly involves cultural fusion. The Ptolemies, though Greek, adopted many Egyptian traditions. They sponsored temples, and Egyptian priests incorporated Greek astronomical symbols into their own cosmology. The Dendera Zodiac may be the result of that synthesis, a hybrid star map that blended two traditions. But what was it really for? Was it a literal star chart, intended to show the configuration of the sky at a particular moment. Some researchers have tried to calculate its date from the alignments of the figures, proposing dates ranging from 700 BC to 50 BC, but no consensus has emerged. Others argue that it was a religious ceiling with astronomical imagery serving allegorical purposes, not precise measurement. The original relief was removed from its ceiling in 1822 and shipped to France, where it sits in the Louvre today. Its removal sparked huge interest in Egyptology, and it remains a tantalizing piece of evidence for how ancient cultures adopted and adapted astronomical knowledge across borders. But the question of whether it is a functional star catalogue or a symbolic cosmology remains unresolved. That puzzle, like the Dendera Zodiac itself, refuses to yield a single answer. But while the Dendera Zodiac leaves us guessing about its specific function, there were ancient instruments built not for ambiguity but for precise measurement. The Armillary sphere is one of the most important of those tools. It consisted of a set of nested bronze rings, each representing a fundamental circle of the sky. The celestial equator, the ecliptic path of the sun and planets, the tropics, and the meridian. By rotating these rings and aligning them with observed stars, an astronomer could read off coordinates directly. The device is often attributed to the great astronomer Hipparchus of Nicaea, who worked in the 2nd century BCE, though it may have been invented earlier by Eratosthenes. What matters is how Hipparchus used it. He compiled the first comprehensive star catalogue in the Western tradition, listing the positions and brightnesses of over 800 stars. That original catalogue is lost, but its data survives because Ptolemy copied it into his Almagest 2 centuries later. The Armillary sphere gave Hipparchus the accuracy he needed to notice something strange. When he compared his measurements of certain stars with records from earlier Babylonian observers, he saw that the positions had shifted slightly over the centuries. The entire sphere of fixed stars appeared to be slowly rotating. He had discovered the precession of the equinoxes, the 26,000-year wobble of Earth's axis. This was a concrete discovery built on precise instrumentation. The Armillary sphere itself was not lost. It was refined and used by Islamic and Chinese astronomers for centuries. But Hipparchus' original catalogue, the direct product of that device, was lost. The Armillary sphere was a powerful tool, but it was also large and stationary, best suited for an observatory. What if you could shrink the entire celestial sphere down to a portable brass disc small enough to hold in one hand? That was the Astrolabe, likely invented in the 2nd century BC, possibly by Hipparchus himself. The Astrolabe used a mathematical trick called stereographic projection to map the 3-dimensional sky onto a flat surface. The result was a device with 2 main parts: a fixed plate engraved with coordinate lines for a specific latitude, and a rotating openwork disk called the rethink that showed the positions of the brightest stars and the ecliptic. By aligning the rethink with the sun or a known star, an observer could read the local time, find the altitude of a celestial body, or determine the time of sunrise and sunset for any day of the year. For the Islamic astronomers who perfected it, the Astrolabe became an essential tool for navigation, calendar keeping, and setting the times of daily prayer. It required not only precision craftsmanship but a deep understanding of spherical geometry, because without that, the projection would have been impossible to design. The Astrolabe represents something crucial to our story, a device that survived, evolved, and spread across continents. But its early Greek origins are often forgotten, overshadowed by the brilliant Islamic examples from later centuries. That survival is itself remarkable, yet it also raises a question. If the Astrolabe could be preserved and improved, what other devices from the same period were not so lucky? The Astrolabe survived, but another device from roughly the same era was built, described in detail, and then lost for centuries before historians recognized what it had achieved. In Song Dynasty China, the scholar and engineer Su Song completed a project that had taken years, a towering astronomical clock standing 12 meters high, powered entirely by water. He described it in a book, the Xin Yixang Feiao, or New Design for an Armillary Sphere and Celestial Globe. That book is the only reason we know what he built. The tower had several levels. At the top sat a rotating armillary sphere whose rings tracked the positions of the sun and moon. Below it, a celestial globe turned in synchrony with the real sky, showing which stars were overhead at any moment. But the real innovation was a massive water wheel at the bottom, driven by a constant flow of water. To keep the wheel from spinning too fast, Su Song designed an escapement, a device that caught the wheel, released it, caught it again, producing regular, controlled motion. That escapement is the earliest known in the world. In Europe, a similar mechanism would not appear for another 200 years. The tower also had time-announcing figures that emerged from doors and struck bells, gongs, and drums at specific intervals. It was a true mechanical clock, driven by hydraulics, linked to the movements of the heavens. Compare this to the Antikythera Mechanism. Both are complex gear-driven machines that modeled the cosmos. But Su Song's device was on a completely different scale. It was a fixed installation, not a portable instrument, and it used water power rather than hand cranking. Yet both represent a level of mechanical and astronomical knowledge that we once assumed was impossible for their times. And both were lost, the Antikythera at the bottom of the sea, Su Song's tower dismantled and scattered during the wars that followed the Song dynasty. The existence of this clock tower forces us to rethink the map of ancient mechanical innovation. The Greeks had their tradition. The Chinese had theirs, independent, equally sophisticated, and equally fragile. The knowledge that built that tower was preserved in a single book and a few diagrams, then reconstructed by modern scholars only in the 20th century. From the lost clock towers of Song Dynasty China, we cross the Pacific to a very different landscape, the coastal desert of Peru. Here, around 300 BC, long before the Inca, a culture built something entirely dedicated to the sun. It is called Chankillo, and it consists of 13 stone towers lined up along a low ridge, spanning roughly 300 meters. From a designated observation point to the west, an observer would see the sunrise appear between different gaps between the towers as the year progressed. On the summer solstice, the sun rose at the far left end. On the winter solstice at the far right, and on the equinoxes, it appeared almost exactly in the center. This is not speculation. The alignment is precise. The 13 towers create a horizon calendar that could mark every few days throughout the year. Chankillo predates similar horizon observatories in Europe by centuries. It shows that the people of the ancient Americas developed sophisticated solar astronomy entirely on their own, without influence from the Old World. Their calendar was carved not into stone but into the landscape itself, using the sun as a clock hand. It is a concrete discovery, a complete, functioning solar observatory built over 2,000 years ago, still standing in the Peruvian desert, and it changes how we understand the reach of ancient science. The Maya of Central America left behind one of the most remarkable astronomical documents ever created. It is called the Dresden Codex, one of only 4 surviving Maya books. Inside it lies a table dedicated entirely to the planet Venus. The Maya recognized Venus as a celestial body with a regular, repeating cycle. It appears as the morning star for 260 days, then vanishes, then reappears as the evening star for another 260 days. From first morning star to the next first morning star, the cycle averages 584 days, but the actual synodic period of Venus is 583.92 days. That tiny difference matters over time. The Maya noticed it and they corrected for it. Their Venus table in the Dresden Codex tracks the planet over a span of 104 years. Within that table, they built in adjustments to keep their predictions aligned with the real sky. They understood that after several cycles, a small correction was needed, subtracting 4 days every 61 years or something similar. The result was a predictive system accurate to within a few hours over a century. This is not astrology. This is applied mathematics tied to a calendar that governed their agriculture, warfare, and rituals. The Maya arrived at this precision entirely independently. No Old World influence, no Greek or Babylonian heritage. Their knowledge was lost when Spanish conquerors burned most of their books in the 16th century. Only the Dresden Codex survived. When modern scholars decoded the Venus table, they had to acknowledge that the Maya understood the motion of a planet with an accuracy that Europe would not achieve until the Renaissance. That is a concrete discovery. Not every ancient astronomical discovery required intricate gearwork or century-spanning tables. The gnomon is just a vertical stick. Its shadow reveals the sun's altitude and direction. Anaximander introduced it to Greece, but its greatest use came with Eratosthenes. On the summer solstice, he observed that in seeing the sun cast no shadow, while in Alexandria it cast an angle of 7.2 degrees. That difference, combined with the measured distance between the cities, let him calculate Earth's circumference to within a few percent. The Chinese also used the gnomon to determine solstices and equinoxes. Because shadow length varies with latitude, this simple device directly demonstrated our planet's curvature. That knowledge, the size of the Earth, was later lost and had to be measured again in the Renaissance. Then there was the triquetrum, a device built not for finding Earth's size but for mapping the stars themselves. Ptolemy, working in Alexandria in the 2nd century CE, needed a way to measure star altitudes with repeatable accuracy. The triquetrum was a hinged rod with a sighting rule and a graduated scale. You aligned the sight with a star, read the angle from the vertical, and recorded that position. It was portable, straightforward, and precise enough to be useful. With instruments like this, Ptolemy compiled the star catalogue in the Almagest, listing over 1,000 stars with their coordinates. The positions were accurate to roughly 1/4 of a degree, a level of precision that made the catalogue a reference for astronomers across the following centuries, whether in Islamic observatories or European universities. The triquetrum itself remained in use, essentially unchanged, for more than 1,000 years. That continuity is revealing. The knowledge embedded in the Almagest was not lost in the same way as the Antikythera gears or the true size of the Earth. Yet the fact that Ptolemy's data stayed relevant for so long underscores something else: how few improvements were made. The triquetrum was a good tool, but it would take another advance, a different kind of instrument, to push the boundaries of what could be measured. While the triquetrum mapped the stars for a catalogue, a different kind of tool had been serving a practical purpose for centuries in Egypt. The merkhets was simple in design. A straight stick, a plumb line, and a sighting piece. You held it upright, aligned the plumb line with a reference mark, and then sighted along the instrument to observe a star crossing the meridian. That single transit told you the hour of the night with surprising accuracy. But the merkhets' real legacy is in what it helped build. Using pairs of merkhets and observing specific stars, Egyptian surveyors could align the sides of the Great Pyramid of Giza to true north within a fraction of a degree. The same method oriented temples and other monuments. This was not symbolic astronomy like the Dendera Zodiac. It was practical, precise, and essential for engineering on a monumental scale. The merkhet shows that the ancient Egyptians turned observation into action, and the evidence is still standing in the desert. In Alexandria, 3rd century BC, Ctesibius built something that blurred the line between tool and machine. His water clock used a carefully regulated flow of water into a tank, where a floating rod rose at a steady rate, moving a pointer across a scale. Small figurines moved at certain hours. Drops of water triggered alarms. According to later descriptions, the clock indicated not just the hour but the changing length of day with the seasons, the position of the sun, and possibly even the phase of the moon. This was an early attempt to automate the cosmos, to turn the sky into a mechanical display that worked without human intervention, combining hydraulics, gearing, and astronomical knowledge centuries before the Antikythera Mechanism. Only through the writings of Vitruvius and a few other ancient authors do we know these details. No complete example survives. The exact gearing, the specific mechanisms, the craftsmanship behind it, all of it is lost. We have the idea but not the device. The ambition to mechanize time and the sky was already alive, but the details, the real engineering, are gone. Ctesibius was not the only one. In the pages of Vitruvius we find another device that pushes the idea further. He calls it the anaphoric clock, essentially a mechanical planisphere. A rotating bronze drum driven by a steady water flow displayed a star map on its surface. As the drum turned, it showed which constellations were rising and setting at any given moment in the night. The map was not a simple picture but a stereographic projection of the celestial sphere onto a flat disk, the same mathematical technique later used in astrolabes. Mapping the entire sky onto a two-dimensional surface while preserving angular relationships requires knowing star coordinates and how to project them. The anaphoric clock combined that projection with a mechanical drive, so the map rotated in sync with the actual sky. Vitruvius attributes the design to Ctesibius himself, or possibly to Andronikos of Syrtis, the architect of the Tower of the Winds in Athens. That tower once housed an anaphoric clock, though only the octagonal building and Vitruvius' description survive. The mechanism is gone, but the description proves that the idea of a mechanical planetarium existed in antiquity, a device that showed hour by hour which stars were overhead without ever looking up. That is the same concept behind a modern planetarium projector, only driven by water instead of electricity. The anaphoric clock was not the only such device. Cicero describes a bronze sphere made by Archimedes more than a century earlier. According to Cicero, that sphere could show the motions of the sun, the moon, and the 5 known planets, not just their positions but their apparent speed and even retrograde loops. It could model a solar eclipse by making the moon pass in front of the sun at the correct moment. In other words, it was a mechanical planetarium. Cicero was not writing science fiction. He was a lawyer describing an object he had probably seen. He says the sphere was so accurate that you could set it to a given date and watch the heavens unfold on its bronze surface. That description, written in a dialogue called On the Republic, has tantalized historians ever since. The only way to achieve that level of simulation with ancient materials is gears, exactly the kind of gear trains the Antikythera Mechanism used. Archimedes' sphere, if it existed, would have been a close relative, perhaps even a direct ancestor, of that shipwreck computer. The sphere was reportedly taken to Rome as war booty after the Roman sack of Syracuse in 212 BC, the same siege that also claimed Archimedes' life. It was admired for generations, then vanished from the historical record. No physical trace survives, but the textual evidence is strong enough that modern engineers have attempted reconstructions, and several plausible models exist using differential gearing. But not all threads of ancient astronomical knowledge were lost. Al-Zarqali, an 11th century astronomer in the Islamic Caliphate of Cordoba, solved a fundamental limitation of the standard astrolabe. That instrument was calibrated for a specific latitude, travel north or south, and the star positions on the retere no longer matched the sky, making the device useless. Al-Zarqali's universal astrolabe used an equatorial stereographic projection. Instead of projecting the sky onto a disk centered on the celestial pole, he projected it onto a plane perpendicular to the celestial equator. That allowed one instrument to work from any latitude on Earth. You simply adjusted the rethink to your local horizon, and the same device could map the sky from Baghdad to Seville to the British Isles. He also compiled the Toledon Tables, a set of astronomical calculations based on years of observations and corrections to earlier Ptolemaic models. Those tables became the definitive reference for European astronomers and navigators for centuries after they were translated into Latin. When later scholars like Copernicus began their work, they were standing on data that Al-Zarqali had refined. In 2nd century China, Zhang Heng built a device the West would not match for nearly 1,000 years. He is remembered for inventing the first seismoscope, but his water-powered armillary sphere was a greater achievement. It was an orrery, a rotating model of the celestial sphere. Zhang Heng took the traditional armillary rings and set them in motion using a steady flow from a water clock. That regulated stream turned a wheel which drove a system of gears. The gears rotated the rings at exactly the same rate as the actual sky. An observer could watch the bronze rings track the sun, moon, planets, and stars in real time, predicting their positions days or weeks in advance. Zhang Heng wrote detailed descriptions of the mechanism, explaining the gear ratios and water flow control. He understood that celestial motions were cyclical and could be replicated mechanically. His device stood in a pavilion in Luoyang, the imperial capital. It maintained the official calendar and forecast astronomical events for the court, but after Zhang Heng's time, the knowledge of how to build it faded. The mechanism was too complex for routine maintenance, and political turmoil in the later Han Dynasty destroyed many imperial workshops. By the Tang Dynasty, his water-powered sphere had become a legend, described in records but unreconstructible. Not until the 11th century, when Su Song built his famous clock tower, did Chinese astronomers again use water power to drive an armillary sphere and celestial globe. Even Su Song's tower was lost after a few decades. The concrete discovery is that Zhang Heng's device represents an independent Chinese invention of mechanical astronomy, centuries before any similar mechanism appeared in Europe. It used the same principles of water regulation and gearing that would later drive Renaissance clocks, yet it was lost within its own civilization, not from ignorance but from fragility, dependent on stable institutions and individual masters who could pass on the craft. When those conditions collapsed, the machine stopped turning, yet some lost knowledge survived in marble. In Naples, the Farnese Atlas, a Roman copy of a Greek statue from the 2nd century BCE, shows the Titan holding a celestial sphere on his shoulders, and the sphere is carved with constellations in detailed relief. For centuries, art historians admired it as a beautiful sculpture, but in the 2000s, astronomers realized it was far more valuable than anyone had recognized. The constellation figures are no random arrangement. They follow a fixed coordinate system. The positions of the stars as marked on the sphere were analyzed and compared with known ancient star catalogs, and the data pointed consistently to one source. The Lost Star Catalogue of Hipparchus, compiled around 129 BCE. Hipparchus had measured the positions of over 800 stars with unprecedented precision using an armillary sphere. That catalogue influenced astronomy for centuries, but the original was lost, surviving only through partial quotations in Ptolemy's Almagest. The Farnese Atlas gives us something the manuscripts cannot. The actual coordinate data frozen in stone. The sphere is not perfectly accurate, but it is accurate enough to reconstruct Hipparchus' observational methods. It shows the celestial equator, the ecliptic, and even the Milky Way as a faint band. The sculptor likely worked from a detailed plan or a globe provided by an astronomer, so the statue is essentially a three-dimensional copy of Hipparchus' data. By measuring the angles between constellations on the sphere, astronomers have been able to estimate the epoch the map represents, and it matches Hipparchus' era almost exactly. This is the only surviving visual representation of what the sky looked like to the most meticulous Greek astronomer. captured not for scientific use but for mythological display. The Farnese Atlas changes the perspective because it reveals that lost knowledge can hide in plain sight. A piece of art made to decorate a Roman villa carries scientific data that was otherwise erased from history. The armillary sphere of Hipparchus is gone, his original star catalogue is gone, but the positions he measured still exist in a sculpture that survived the fall of Rome, the Middle Ages, and the Renaissance. And that is the paradox of lost scientific knowledge. The Farnese Atlas was never meant to be a scientific instrument. It was a mythological decoration for a Roman villa. Yet it preserved Hipparchus's star positions so faithfully that astronomers can still read them today. It survived because no one tried to destroy it. It simply outlasted the empire that built it. Each of the 18 devices we have traced tells a similar story. From the Antikythera Mechanism to the Maya Venus tables to Su Song's water-powered clock tower, each was sophisticated, real, and eventually forgotten. Some were lost through cataclysm, others through neglect, a few deliberately destroyed. Together they prove that ancient civilizations understood the cosmos far more deeply than our textbooks once admitted. That understanding was not a straight line of progress. It was a tapestry woven in flashes of brilliance across thousands of years and thousands of kilometers. The real lost knowledge is not just the devices themselves. It is the methods, the philosophy, the craftsmanship that made them possible, the accumulated experience of generations of observers, the tacit knowledge of metalworkers and astronomers, the mathematical frameworks passed from master to student. When those chains of transmission broke through war, plague, or political collapse, the knowledge vanished as if it had never existed. We are only beginning to reconstruct it from fragments. A corroded gear, a clay tablet, a carved stone globe. The Farnese Atlas brings this into focus. It is not a functional device, but it carries functional data. It reminds us that knowledge can hide in plain sight, and that we may still be surrounded by lost science without recognizing it. Which of these ancient devices surprises you the most? And do you think there are even more advanced ancient technologies still buried beneath the sand or sea, waiting to be found? Subscribe to join us every week as we uncover the forgotten stories and hidden achievements of the ancient world.